PyTorch is the library that powers almost every modern language model, from ChatGPT to Llama to Stable Diffusion. And the reason it won is beautifully simple. It feels just like writing normal Python. So in this video, we're going to build that intuition from the ground up. We'll start with tensors and automatic gradients, build a neural network, train it, and then assemble the actual pieces of a transformer, the architecture behind every large language model. Every step we'll write real PyTorch code and see what it prints. Let's go. First installation, PyTorch is just a pip package. We install it, then confirm it imported and check the version. That single import torch, unlocks everything we'll use today. Everything in PyTorch is a tensor. A tensor is just a multidimensional array like a NumPy array, but with two superpowers. It can run on the GPU and it can track gradients. Here we make a 2x3 tensor from a nested Python list. Printing it shows the values. The shape tells us it has 2 rows and 3 columns. The D-type is int64 by default, and the device is CPU because right now we're not on a GPU. Shape, D-type, device. You'll check these 3 constantly. You rarely build tensors by hand. PyTorch gives you constructors for common shapes, zeros for all 0, ones for all 1, and arrange for a range of values here, even numbers from 0 to 8. Operations work just like math. Multiply a tensor by 2, add 1, and PyTorch applies it element-wise. Every operation returns a new tensor and they chain naturally into expressions. This is the normal Python feeling that makes PyTorch easy to pick up. Here's superpower number 1, the GPU. We pick a device string CUDA if a GPU is available, otherwise CPU. Then random creates a 4x4 tensor of random numbers and dot-to-device moves it onto that hardware. The same code runs on a laptop or on an 8-GPU server, only the device string changes. On this machine there's no GPU, so it stays on CPU, but the pattern is what matters: create then move. Now superpower number 2, and the big one, automatic gradients. We make a tensor x equal to 2 and we tell PyTorch to track its operations by setting requiresgrad equals true. Then we build an expression x squared plus 3x plus 1. PyTorch records every operation into a computation graph behind the scenes. When we call dot backward, it walks that graph backwards and fills in the derivative. For y equals x squared plus 3x plus 1, the derivative is 2x plus 3, at x equals 2, that's 7. We didn't derive it by hand. PyTorch did. That is the heart of deep learning. You define a function, PyTorch gives you its slope, and you use that slope to improve your model. So here's how training actually works. Picture your model's error as a landscape with hills and valleys. High up is bad, the bottom of the valley is good. Each gradient tells you which direction is uphill, so you step in the opposite direction, downhill, take a step, recompute the gradient, step again, over and over. That's gradient descent. Autograd computes the slope, the optimizer takes the step, and slowly you roll down to the minimum. Every neural network you've ever used was trained this way. To build a model, use subclass nn.Module. In init you declare your layers, here a linear layer mapping 4 inputs to 16, then another mapping 16 down to 1 plus a REALU activation. In the forward method you define how data flows through them. Input goes through FC1, gets activated by REALU, then passes through FC2 to produce an output. Instantiate the class and print it. PyTorch lays out the whole architecture for you. This tiny network is already a real, trainable neural net. Every model from a classifier to GPT is built this way. And here is the training loop, the same 5 lines that train every model on Earth. First, a loss function and an optimizer. MSE loss measures error, SGD updates the weights. We make some fake data, then loop. Each step, run the model to get a prediction, compute the loss, call zeograd to clear old gradients, backward to compute new ones, and step to update the weights. Print the loss each epoch and watch it fall from 1.2 down to 0.85. The model is learning. Memorize these 5 lines, everything else is scale and architecture. Now we begin building a language model. Step 1, text isn't numbers, so we turn tokens into vectors using an embedding layer. We give it a vocabulary of 4 words and an embedding dimension of 8. Each token id 0 for the 1 for cat and so on gets looked up into its own 8-number vector. In goes a 1x4 list of ids, out comes a 1x4x8 tensor of vectors. These vectors are learned during training and they're what let a model capture meaning. Embeddings are the bridge from words to math. The transformer's secret is self-attention. Each token looks at every other token and decides how much to care about each one. We form 3 views of the input: queries, keys, and values. Scores are the queries times the keys, measuring how relevant each pair is. We scale by the square root of the dimension for stability. Softmax turns scores into weights that sum to 1, and we multiply by the values to get the output. Here the word cat attends to itself most, 41%, but also reaches to the insat. Attention is how a model understands context. Now we assemble a full transformer block. It has 4 pieces. Multihead attention lets every token attend to all the others. A feed-forward network linear GLU linear processes each position, and 2 layer norms with residual connections. We add the input back before normalizing, shown as x plus a and x plus f residuals let gradients flow deeply so the network can be stacked. Instantiate it with dimension 8 and 2 heads and you get 1400 parameters, a real modern transformer block. Stack a dozen of these and you have a small GPT. Finally, generation. Language models are autoregressive. They predict 1 token at a time, then feed it back in. We start with 3 IDs, the cat sat. In a loop, embed the sequence, run it through our transformer block, project the last hidden state to logits over the vocabulary, and take argmax to pick the most likely next token. Concatenate it onto the sequence and repeat. 4 steps gives us 4 new tokens. That is exactly how ChatGPT answers you: generate, append, repeat, just with a much bigger model and a smarter sampling. So that's the full journey in Real PyTorch. We started with tensors, the arrays that hold all data. Autograd gave us automatic gradients, the engine of learning. We built models with nn.Module and trained them with that 5-line loop. Then we climbed into language models, embeddings to turn words into vectors, self-attention to capture context, a transformer block with residuals and feed-forward layers, and finally an autoregressive loop to generate text. Every large language model is exactly these pieces scaled up. PyTorch didn't just make this possible, it made it readable. Tensors, gradients, modules, training, transformer, that's PyTorch. Thanks for watching.